Okay, let's start. So turn on video. Okay, so today we do chapter 5, the 5.1 and 5.2. So I at first finished the one sample t-test. Then we study the Wilcoxon rank sum test, Wilcoxon signed rank test, sorry. So yeah, one sample t-test has been done in STAT 2210, but Wilcoxon test maybe have not been covered in STAT 2210. Maybe it has been covered. Yeah, so we have to do this. Probably we don't have enough time for exercises today, so we do next time. And homework 1. I have some concern about homework 1. So actually we have 18 submissions and 10 missing homework 1. And as long as you submitted homework 1, basically almost all of you did well. So don't worry too much. But if you have not submitted homework 1, because you have difficulty for our coding, that is, I think, a problem. So if you didn't have enough time to learn our language, then you will catch up. That's still fine. But if you really have a difficulty for our coding, or you don't have much time to catch up later, then possibly it may be a good idea to drop the course. Okay. And yeah, but as long as you have submitted, then you did well. So I have already graded today. So I think the majority of students get 8 point or more. Yeah, so that's it. And yeah, so I will share the screen and start chapter 5 again. Do you have any questions for homework or anything else? Yeah, homework 2 is just accidentally similar to exercises, so you won't have much trouble. And probably we'll have the homework 3 1 week later. So we will have 3 homework before the midterm 1. Sorry. Okay. Oh, I think I got is the rubric. Yeah, I think the homework 1 score is already available, and I commented in Canvas. So if you have 5 pages of PDF files, probably I will comment maybe a couple of places, especially if you didn't get the full score. Yeah, you can check it out, and if you have any questions, just let me know. Okay, so we started the chapter 5 last time, and we did one sample t-test. Oh, sorry, homework 2 problem 1. Does mean absolute value use sample mean or arithmetic mean? Homework 2, I think the mean absolute value, I think I gave the equation. So use n, I think that is the short answer. Just let me see the homework 2. Okay. Yeah, let me see. Homework 2. Yeah, I think it specifically mentioned that the mean absolute deviation is defined by 1 over n times the summation. So 1 over n, yes. And x bar is mean. the sample mean, arithmetic mean, those are the same, right? Mean. We can say sample mean. Oh, yeah. Okay, so yeah, that's it. And chapter 5, we are studying hypothesis testing. So hypothesis testing is decision-making problem between null hypothesis and alternative hypothesis. So binary decision-making. And those two decisions are not symmetric because we only reject H0. We reject H0 only if we have strong evidence to reject H0. So H0 is null hypothesis. So usually we want to reject that null hypothesis. If you cannot reject, then basically our conclusion is 0. So that's why we say it's a null hypothesis. So if H0 is rejected, we can strongly claim that H1 is true. But if H0 is not rejected, maybe H0 is true, maybe H1 is true. So our conclusion is not strong. And yeah, last time we discussed this example and how to test quantity. And basically the idea is represented in this slide. So under H0, we construct some test statistic like T here. And under H0, null hypothesis, we have distribution of T. And mostly the value should be around here. Okay? But if the value falls in very extreme range of this distribution, we consider that this is the counter evidence against H0. So we reject H0. So that is the idea. So we construct some test statistic, and if test statistic, we have distribution of test statistic under null hypothesis. If the realization of test statistic is a very extreme value, then we reject H0. So that is our idea of hypothesis testing. And yeah, actually we constructed this T statistic, then we do tests. And in our example, our realization is just one typical value of this distribution, so we cannot reject H0. And we defined several notation, T sub alpha and Z sub alpha. And T sub alpha is the quantile point, that the area under the curve below this point is exactly equal to alpha. So the probability of test statistic falls in this shadowed area is T sub alpha, T sub alpha with degrees of freedom n here. And this is symmetric distribution. So T sub 1 minus alpha is just the other side. And Z sub alpha is used for normal distribution. And here is some examples. So what is T sub 0.025 of degrees of freedom 6? That is quantile function of 0.025 df6. Then that is this point. Sorry, this is actually normal case, but for T case, negative 2.44. And normal case, the same thing. So QT function, Q normal function calculates the T sub alpha or Z sub alpha. So overall, the testing scheme is here. So we have the H0 and H1. We are considering a sample whose value is continuous. So last time that we test if the average mass PhD student salary, a PhD graduate salary is equal to $79,500 or different from that. And once we construct T statistic, basically this reflects the deviation from the 79,500. If this falls in this center range, then we do not reject the null hypothesis H0. And if it falls in this shadowed area, we reject H0. So important thing is this rejection region, so-called rejection region, is just the two sides of the distribution. because if mu is different from mu naught, that means the mu is much larger than mu naught, or mu is much smaller than mu naught, then we should reject H naught. So that's why if T statistic is much smaller than 0 or much larger than 0, we reject null hypothesis. And usually we set significance level as 1% or 5%. This is basically the area, the shadowed area. So we either reject null hypothesis if the T statistic fall in the extreme 5% range or extreme 1% range. Yeah, you can change this number into 0.1 or 0.02, but usually, conventionally, we use the 5% or 1%. And the next one is one-sided test. So one-sided test, the alternative hypothesis is different. So alternative hypothesis is just less than mu naught. Sometimes this is the other way, but the less than mu naught. This is one example of one-sided test. So in null hypothesis, we assume that mass PhD's salary for maybe entire university within the entire department, that is equal to 79,500. This is the null hypothesis. And alternative is mu is less than 97,500. So we do not consider any possibility that mass PhD's salary is more than overall PhD salary. So this is we assume this never happens. We implicitly assume that so this never happens. So one-sided test is based on stronger assumption than two-sided test. And in this case, we reject null hypothesis if T is less than T sub alpha n minus 1. So, okay, so let's see if we have the T distribution, and this is a density. And the T distribution is like this. And if T statistic falls in lower 5% range, then we reject. So this range is rejection region. So we reject H naught. If T statistic falls in this range, we reject H naught, and otherwise we accept H naught. So this is only one side of the distribution. Because the alternative hypothesis is mu is less than 79,500. So that means that if H1 is true, then T statistic should be much smaller than 0. So T statistic is basically our sample mean minus this 79,500 divided by some quantity, that's S over square root of n or something. So if X bar is much smaller than 79,500, then T statistic is much smaller than 0. So we want to reject H naught only if there's such case. For example, if X bar is much larger than 79,500, that supports H naught compared to H1. So we should reject the null hypothesis if T statistic is small enough. So in this case, the threshold is 5%, the fifth percentile. So that is negative 1.943. So the idea is to reject H naught if T falls in the smallest 5% range. Yeah. And the definition of H naught and H1 presumes that the mu is never larger than mu naught. Yeah, so here. And yeah, actually for two-sided test, we just use the 2.5% lower range and the 2.5% higher range. So 2.5% becomes 5%. So actually, as long as T is negative, it's easier to reject null hypothesis because we have strong assumption that the mu is never larger than 79,500. So okay, so which case we should use two-sided test and which case we should use one-sided test. And my recommendation is they use two-sided test if you don't have specific reasons. Okay. So we have the one-sided test has stronger assumption. So people can criticize your assumption. So if you don't have any reason, they always do two-sided test. You have some logical reason that mu is never larger than 79,500, then you can do one-sided test. So mostly that you can do two-sided test. And yeah, so this is the case that H1 is mu is smaller than mu naught, but the other way around is also possible. In such a case, rejection region is the other way. So we only reject null hypothesis if T statistic is largest 5% range. So this is the rejection region for this case. Any questions? For the distribution is the variable in the numerator of the fraction of the same as. For the distribution, not sure what this is question. For the distribution, not sure. So yes, so we consider just entire quantity T. So yeah, so denominator, the numerator divided by the denominator is the problem. Right? Okay. Yeah, so now the code, our code for t-test. So maybe theory is a little complicated, but the code is very simple. So your advantage will be understanding theory. So using code can be done by basically anyone, especially for this kind of ready-made function. So t.test. So t.test, the income includes the, I think the 7 math PhD's salary, and the mu is equal to 79,500. So this specifies the null hypothesis. Then we have this result. So t statistic negative 0.94. That is what we got. And the df, degrees of freedom, is 6. This is sample size -1. And p-value 0.38. So that is what? This is just the area. So this is, I believe, two-sided test. So that means this area plus this area. The total area is 0.38. So that is this output means. Yeah, so this 0.38 means this area. And I will explain later about the confidence interval. So the mass PhD's salary for the entire department in the long run, that is between 46,900 to 93,800. So that is the range, so confidence interval. We are 95% confident about it. And this is just a sample mean of mass PhD salary, so X bar. Yeah, so just the t.test function of this. This did the one sample t-test with two-sided alternative, two-sided test. So now we study the concept of p-value. So p-value may be covered by the stat 2210, but we will review it. Okay, I got another question. The formula for the distribution is f is equal to x sub m x sub, not sure. So yeah, I think Kevin, you can ask a question after the class. Sorry, we don't have m still yet. So yeah, maybe you can ask a question later. And p-values, yeah, so we have significance level that when we do sample t-test, the one sample t-test. So alpha maybe 0.01, alpha maybe 0.05. If the 0.01 that we have much smaller rejection region, for example, if we have this distribution and this distribution and what's the rejection region. So if alpha is 0.01, the rejection region is very small. 5% rejection region is very large. And one problem is, different people may want to have different alpha. So in such a case, every time you have to specify this significance level alpha. That is sometimes inconvenient. So we calculate the p-value. So p-value is actually the probability that more extreme event happens compared to more extreme event than our sample happens. So, sorry, I want to. Okay, so rejection region is these two, but the p-value, the concept of p-value is once we observe our test statistic t, then we calculate the total area of this. So this total area is called p-value. So if this total area is less than 5%, less than 0.05, we will reject H0 with alpha is equal to 0.05. Okay. So if we see p-value, basically it can be used for anyone. So we can test with any significance level. So the reporting p-value is more informative than just getting results, such as we reject null hypothesis at alpha is equal to 0.05. So yeah, that is the idea of p-value. So p-value is this area if the test is two-sided. If one-sided, the p-value is just the one side of the area. So this is two-sided case. So maybe I would say this is 1, 2, 3. Then the case 1, we have this. And the case 2, we have p-value defined by this area. Okay, so this is different t, but this area. Maybe to avoid confusion, maybe I on purpose to make t value obviously different. So this is p-value for case 2. So if two-sided test, the p-value corresponds to the two-sided the probability. And if one-sided test, the p-value is just one side of the distribution. Okay. So yeah, so that's it. And the p-value is always between 0 and 1 because this is the area. If, for example, in the second case, if the t value is even -1 around here, then p-value is maybe 0.97 or 98. So it gets much larger. But anyway, p-value is probability, so between 0 and 1. So p-value represents the probability that a more extreme event than t happens under H0. So in general, the H0 is rejected if and only if p-value is less than alpha. So this is very important sentence. So we will study many different tests, but the p-value is always the same. So p-value always has the same definition. So if we have many tests, Wilcoxon rank sum test and the test for variance, chi-square test, we have many tests, but always p-value is defined in the same way. So if you don't know the t-test, you cannot interpret t-statistic. If you don't know chi-square test, you cannot interpret chi-square test. But p-value is always the same. P-value always has the same meaning. So if you see some unknown test, still that you can interpret the test result. If p-value is equal to 0.001, then we have strong evidence to reject H0. So usually the computer output does not say whether H0 is rejected. Rather, the test reports the p-value. So actually, you can see the p-value here, and we can just compare our significance level, for example, 0.005. Our p-value is larger than this, so not reject H0. Okay. Any questions so far? Okay. So yeah, this is the equation to calculate p-value. So last time, our test statistic is negative 0.94. So if the probability of the t statistic is larger than 0.94 or smaller than negative 0.94, that is represented by this, that is the p-value. So that is actually the 2 times probability of t is larger than 0.946, right? So we are calculating the 2 tail probabilities. So that we have the negative 0.94, then we have the positive opponent. And if you calculate this area, say C, then 2C is the p-value. Because this is also C. So this probability is C. Yeah, and t-test can be done by t.test function, but of course that we can do everything from scratch. We can calculate the sample size, that is the length of income. Income have 7 observations, so n becomes 7. And the degrees of freedom is n-1, so 6. And we can calculate the t-statistic by mean minus our null hypothesis divided by standard deviation of income divided by square root of n. So this is the t-statistic, and you can set the threshold. This is the threshold for rejecting alpha is not with 5% significance level. And p-value can be calculated by 2 times just the one-side probability, that is 1 minus pt. Then you can get n and degrees of freedom, and you can get the t-statistic, and you can get the threshold for rejection region, and you can get p-value, and this is the x-bar sample mean. Yep. And yeah, that is the theory. And another example here. Okay, so the average systolic blood pressure of hypertension patients in the hospital is 162.6 millimeter Hg. And 10 patients in the hospital took the prescription, and their blood pressure after 4 weeks are these 10 numbers. And test if the blood pressure decreased significantly after taking the prescription. And so suppose that we are specifically asked to do one-sided t-test, then null hypothesis is mu is equal to 162.6, and the alternative is mu is less than 162.6. Yeah, actually the conventionally, if the sentence mentioned the decreased significantly, then we should go one-sided test. But this could be criticized because this drug may increase the blood pressure, right? So I think it's not scientific to assume that mu is never larger than this original level. But maybe in some cases, it's reasonable to test this mu naught against this H naught against this H1. Okay, so we define vector x, then we can do the t-test by t-dot test function. So here only the difference is we set the alternative here. Alternative hypothesis is mu is less than 162.6. Yeah, then we get the t-value, that is the negative 2.16, and df9 because sample size is 10, and p-value is 0.029. So that means that we have t distribution here, and our realization is around here, and this area is 0.0295. And this is our test statistic. And this is one-sided test, and the mu is less than 162.6 is the alternative. So this number is less than 5%, so we can reject H naught. H naught is rejected with significance level 0.05 because p-value is less than alpha. Questions? Okay, so confidence interval. In the previous t-dot test output, that we have the confidence interval, I think about 47,000 to 90 something, so 94,000, no, 47 to 94,000 in mass PhD example, mass PhD salary example. So this is 95% confidence band. So that means that we only have 7 observations of mass PhD salaries, but if we have survey to get entire population's the average salary, that should fall in this range with 95% confidence. So that is the meaning. But this is a little bit confusing because think about this sentence. The probability of mu is between this 47,000 and 94,000 is equal to 0.95. And mu is just the population mean. This is a constant. And of course, this is a number, so this is constant. And this is also constant. So there is no room to calculate probability. So this sentence is either true or false. And we can never judge the probability of this. So then what confidence interval means? That is interpreted as this way. So we calculated the 47,000 and 94,000 from our sample. So we have some formula to calculate this one and this one. And this depends on our sample. So if numbers depend on sample, that those are random variables. So actually, these A and B are random variables. So okay, so mu is the true parameter. So this is a constant, but we calculate A and B by our sample. So these are random variables. So before observing our sample, actually, this statement makes sense. The probability of mu is between A and B is equal to 0.95. So that makes sense. So, when we write this sentence, it sounds like mu is random and it, mu has some distribution and between constant A and B, but actually not. Actually, the mu is a constant and A and B are random variables. So in this sense that we can, so this sentence makes sense. So probability, mu is between A and B with probability 1 minus alpha. A and B are calculated by some rule using our observations x1 to xn. So to be exact, the situation is like this. So suppose that we have possible parameter space mu, and we have the true parameter. Sorry. We have confidence interval, right? So our confidence interval is from 40. Okay, so maybe we have the 50,000, 60,000, 70,000, 80,000, 90,000, and 100K, and so on. And our confidence interval is from 47 to 94. So actually, our confidence interval, maybe we can write 47 to 94. So like this. And this is based on our sample, say sample 1. If we have another sample, say sample 2, then we have different confidence interval. So different confidence interval may be here. If we have sample 3, the confidence interval is here. And confidence interval maybe here, and maybe here, and maybe here. And 95% confidence interval, that means that the true mean, for example, suppose the true mass PhD average salary is here, then 95% of this range covers this blue point. So occasionally, maybe it misses like this. But the most of the confidence intervals includes the true parameter. So this is the meaning of confidence interval. So in this case, okay, so I write the 10 confidence intervals, and actually this one misses true parameter, but the other 9 includes the true parameter. Sorry, maybe I have, yeah, 10. Okay. So in this case, actually the 9 over 10 confidence interval include true parameter mu. And if we have many confidence intervals, maybe 100 confidence intervals, we expect about 95, maybe 94 or 96. The about 95 that includes the true parameter mu. So that is the meaning of confidence interval. So the confidence interval is calculated by some rule using our observations. And this rule includes the true parameter with, this range includes true parameter with 95% probability. So that's the meaning of the confidence interval. Yeah. And confidence interval is a little complicated because A and B are not really unique pair. So it's possible that the mu is between this and this with 95% probability, but also between A2 and B2 is also 95% probability. Okay. Yeah. So for example, mu is between, yeah, we can say that the mu is between 60K to 120K with 95% probability, but also we can say probability of mu is between 50K to 95K is 95%. So if A1 is larger and B1 is also, sorry, A2 is larger than A1 and B2 is also larger than B1, it's possible that both have 95% probability. So actually the confidence interval is not unique, but usually the shortest confidence interval is most informative. Right? So basically we choose the shortest confidence interval to report the confidence interval. Yeah, so this is just one simple case. Suppose we only have one observation of X from normal mu1. Then we can say that the X plus minus 1.96 covers mu 95% of the time, right? So that is true. But also that you can say the mu is between x minus 2.33 to x plus 1.75. But this one, the range is 2.33 minus 2.33 minus negative 1.75. So this is equal to 4.08. But this one, the range is, you can see 1.96 minus negative 1.96. So this is the 3.92. So this is shorter. So usually that we use this confidence interval. So usually that is symmetric around the mean estimate. Yeah. Any questions? Yeah, so in general, we can say that the confidence interval for mu is described by x bar minus t sub 1 minus alpha over 2 times s over square root of n. S is standard deviation, sample standard deviation. And the upper bound of this confidence interval is x bar plus the t sub 1 minus alpha over 2 times s over square root of n. Maybe I should say that this one is t sub 1 minus alpha over 2 of n minus 1. Yeah, I just wrote in this way because in previous year, the one student was confused by this is always a product of two numbers or not. So just because of that, I express in this way. So now it's clear that probability of mu is between this quantity and this quantity makes sense, right? So A and B are random variables. So it makes sense that probability of mu is between A and B is equal to 90, actually alpha, 1 minus alpha. And actually we can prove this confidence interval. So that is this. So x1 to xn follows normal, the mu sigma square. This is our assumption. Then we can say that the x bar follows the normal distribution with mean mu and the standard deviation, sorry, the variance, sigma square over n. Yeah, you can prove this because the variance of x bar is equal to variance of the x1 plus x2 plus up to xn. I mean, this assumption is IID. So then n. So this becomes 1 over n squared times the variance of x1 plus variance of xn. And this is equal to 1 over n squared sigma square times n. So this is sigma square over n. So we can get this. Yeah, x bar, mean of x bar is still mu. So this is almost clear. Then we divide we subtract mu and divide by s over square root of n. And this follows t distribution with degrees of freedom n minus 1. We haven't proved it, but we have already introduced this theorem. Then that means this entire quantity is between negative t sub 1 minus alpha over 2 to positive t sub 1 minus alpha over 2. You can see that we have t distribution here. Yeah. And if we see the t sub 1 minus alpha over 2, and we have negative t sub 1 minus alpha over 2, then this quantity, this is t statistic. So t statistic is within this range with probability 1 minus alpha. So this probability is alpha over 2. This probability is alpha over 2. Then now we flip the relationship. Actually, this first inequality corresponds to this inequality. So at first, we move, maybe at first, we multiply this term, so on both sides. So then we multiply this, right? And this is this times this. Then we move negative mu to the other side, negative mu to the other side, and we move this quantity to right-hand side. Then we can get this inequality, right? So mu is smaller than x bar plus the t sub alpha 1 minus alpha over 2 times s over square root of n. So that is the our derivation of this. And the other one, the other equation, so this inequality corresponds to this inequality. Then we can say mu is between this random variable and this one random variable with probability 1 minus alpha. So this is the proof for confidence interval. Must the confidence interval be an interval? Can the confidence interval be some more complicated set? That's a good question. And I have never seen the confidence interval is not an interval. And in higher dimensional case, the confidence region has more complicated shape. Usually it's an ellipse, but I think possibly it's a different shape. But most of the time, the confidence interval there should have. I think that always confidence interval should be an interval, and the confidence region. If we have multiple parameters, then confidence region is usually ellipse, but sometimes not. Yeah. Yeah, of course. Yeah, it's possible to consider split confidence interval. Yeah, yeah, that's possible. That's possible. But usually we don't see that case. Yeah, we don't see that case. Yeah. Yeah, maybe the more I can talk about it, but basically statistical theory is not that general and not that logical. If you see the p-value definition of p-value, p-value is the probability that more extreme event than our sample happens, right? But what do you mean more extreme event? Actually, you cannot really define it clearly. So we have some vague argument. So our assumption is the distribution of the test statistics has some simple, mound shaped. Then we can somewhat reasonably calculate p-value. So that is the truth. Like a distribution with do bumps. Yes, yeah, you're right. But if test statistic has distribution with 2 bumps, it's really hard to interpret test statistic. So that's why we haven't seen any confidence intervals, split confidence intervals, right? So yeah, I think that's a very good question. So suppose that we define some test statistic, say what, maybe test statistic like D or something. Then suppose that we have this kind of distribution. Then where we set the rejection region, it's really hard, right? Maybe even more extreme case. Okay, so maybe even more extreme case. Like this. So suppose the distribution of test statistic D has this. Where is the rejection region? So it's not really clear. Maybe we set combination of this and this and this as a rejection region. Yeah, that's possible. But the rejection region is not always defined by the height of this distribution at the density function. So usually this is not really good test statistic. Usually when we see test statistic, the large value reject H0 or small value reject H0 or just the, large or small value reject H0. And we don't want to make it the more complicated. So in this case, rather than considering more complicated testing scheme, we should develop a better test statistic. That is the approach. Yeah. Yeah. So yeah, the parser has very good sense of statistics. Yeah, but the statistics, usually test statistics shouldn't be that complicated. So that is the practical reason that confidence interval is not split. Okay. And confidence interval can be calculated from the formula. And manually, we can calculate this way. This is T sub 1 minus alpha over 2. Alpha is equal to 0.05. And this is standard deviation. And this is square root of sample size n. Then you can get this number. And upper limit, we have this number. Yep. Yeah, very good question. Yeah, parser asked. Yeah, actually, the definition of p-value is not really mathematically 100% logical, and the allowed test statistics are very limited. So those are the facts. Okay, and the next one is the Wilcoxon rank sum signed rank test. Sorry, we have two tests: Wilcoxon signed rank test and rank sum test. But here we study the Wilcoxon signed rank test. And yeah, the theory is a little bit complicated. So I will have one example, but the basic idea is that the t-test is based on normal assumption of variable, but that is not always satisfied. So we want to have a test based on weaker assumption. And I will go from this example. So suppose that we don't know at all that this data follows normal distribution. And still we want to test if the center of that value is 79,500. I would say center because we even don't know whether population mean exists, right? So some distribution, heavy-tailed distribution, may not have the population mean. Yeah, but the idea of this test is only considering ranks of observations. So we have these 7 observations, right? And we are comparing these observations with this 79,500. So we subtract the 79,500 from each observation. So 55,000 minus 79,500 is negative 34,500. Next one, 80,000 minus this is 500, and so on. So we can calculate these values. And these are deviation from 79,500, the null hypothesis. So if null hypothesis is true, then these numbers are randomly distributed on both sides of 0. And now that we rank these observations in terms of absolute value. So you can see 500 is smallest. So this is 1. And the next smallest one is negative 14,500 in terms of absolute value. So this is 2. But we put negative sign because we have negative sign here. So for negative signs that we put negative. Yeah. And in this way, okay, so we have numbers and the sum of the positive numbers, we can say sum of the positive numbers, that is 1 and 3 and 5, that is 9. And the sum of the negative numbers, that is negative 7, negative 4, negative 2, negative 6, that is 19. If 79,500 is just the center, then these two numbers, they should have similar values. The V and V asterisk should be similar numbers. So that is the idea. But the summation of V and V asterisk is always 28 because this is summation of 1 to 7. Right? Summation of 1 to 7 is equal to 7 times 7 plus 1 divided by 2. So this is 28. So summation is always 28. So if the one number is much smaller than the other, then it's not likely that the center is 79,500. Right? So our test statistic is here. Test statistic is the minimum of V and V asterisk. If this is very small number, we reject H0. So that is the idea of Wilcoxon rank sum test. And our assumption is this observation follows some symmetric distribution around the center. Okay. This may not be mu, but some number may be mu asterisk. So this is the distribution of the data. And based on this assumption, we can calculate the distribution of this minimum of V and V asterisk. We can simulate this many times. We simulate 7 random numbers centered at 79,500 many times. Then we calculate V and V asterisk many times. Then we can calculate the distribution of this minimum of V and V asterisk. So we can simulate. We can get distribution of this by simulation under null hypothesis. Then we can calculate, for example, the probability of V is less than 2. Oh, sorry, this is not really V, but yeah, anyway, so we can calculate the probability. We can calculate the distribution of V and distribution of V star as well. So we can calculate when probability, we can calculate the probability of V is less than 2, or V is less than 3, or V is less than 4, and so on. And actually for this case, the V is less than or equal to 2 has probability less than 2.5%. V is less than 3, V is 3 or less, that probability is between 2.5% and 5%. So maybe 3% or 4%. And V is less than or equal to 4, this is a little larger than 5%. And then also we can calculate the other one. So probability of V asterisk is smaller than 2, or V asterisk is smaller than 3 or something. Then finally, we can calculate the probability of minimum of V and V asterisk is less than 2. And actually, from this equation, we can get this equation as well because it's symmetric. Our assumption is distribution is symmetric. So we can get this number. So this means that if minimum of V and V asterisk is less than 2, then we reject null hypothesis. And if not, we do not reject null hypothesis. So that is our two-sided, the signed rank test. So in our case, actually the minimum of V and V asterisk is equal to 9. So minimum of this is less than 9. That probability is pretty large, so we cannot reject null hypothesis. If test is one-sided, to be clear, is V the summation of the signed ranks? Yeah, V is here. So V is the summation of positive ranks. So you can see these ranks, right? So we have some positive one and a negative one, and the V is the sum of positive ranks. So positive ranks is the ranks given for these positive deviations. And V asterisk is the sum of negative ranks. Yep. Yeah, and one-sided test also can be defined. And one-sided test only reject when V is smaller than something, because the alternative, under alternative, the V becomes small, right? So under alternative, mu is smaller than mu naught. So that means that we have the very small percentage of numbers exceeds mu naught. So the V becomes small, and we reject the V is smaller than something. And you can see probability of V is less than 3 is less than 5%. So we reject H naught if V is less than 3%, if alpha is equal to 0.05. So we are talking about 5% significance level here. So this is the testing scheme. So infinite data points. Statistics is everything finite, so that we don't consider infinitely many observations. Yeah, that may be different from engineering. Okay, so the theory for the Wilcoxon rank sum test is here. So signed rank test is here. So basically, that we don't need assumption of normality. So observations maybe follows the skewed distribution or something like that. Skewed, but actually still we have to assume that distribution is symmetric. So the distribution may be not normal. The more like uniform distribution or more heavy-tailed distribution like t-distribution. And in such a case that we can use the Wilcoxon signed rank test, and test only assumes that the symmetry of distribution of the observations under null hypothesis. And this test is robust against violation of normality. And on the other hand, this test has a lower power than one sample test. So we have less assumptions, right? So when we have less assumptions, always our conclusion is weak because we have to consider, more possibilities. So if we can do t-test, the t-test assumption is satisfied, then we should do t-test to get stronger result. If we really cannot do t-test, then we can do a Wilcoxon signed rank test. Yeah, and actually the Wilcoxon signed rank test is used even if distribution is not symmetric. I don't know if it is justified or not. Maybe, at least we don't have normal assumptions, so it's slightly better to apply Wilcoxon signed rank test. But I don't know if that custom is mathematically justified. Yep. And the theorem. Suppose that x1 to xn are IID, continuous random variables, and we want to test if x follows distribution symmetric around mu naught with significance level alpha. We at first defined the signed rank. So basically we rank xi minus mu naught. So mu naught was 79,500 and xi is each observation in increasing order, and the multiplied by 1 if positive, multiplied by -1 if it's negative. And we calculate the positive ranks, sum of positive ranks, and the sum of negative ranks. Then the V does not depend on the distribution of xi's. Yeah. I think that this distribution is not symmetric like this. Suppose that mu naught is somewhere. Oh, sorry. If not symmetric, it affects rank. So probably the Wilcoxon signed rank test is not justified. But still, if it's not normal, it's at least better to use signed rank test. And so, yeah, yes. And V and V asterisk, the sum up to the n over n plus 1 over 2, because this is the summation of I is equal to 1 to ni. So smaller, yeah. So the minimum of V and V asterisk is a good statistic, because if one is small, that means the other is large. So difference between V and V asterisk is large. So that means the more observation on one side. And the p-value is defined by this statistic, minimum of V and V asterisk. So at first we found the this is how to define p-value. So if we observe the lowercase v, this is our test statistic for specific observation, specific sample. Then p-value is defined by probability of minimum of v and v star smaller than our observed the test statistic. And when we calculate, we do two-sided test. We have to consider the two side of the distribution of this test statistic. So we have to multiply by 2 to get p-value. And one-sided test, that is just one side. So v is smaller than v, then this is the p-value. So if this is less than 0.05, we reject null hypothesis. So v is actually the positive ranks, right? So v is positive ranks. So if we have some distribution of this and the capital V is small, that is observations are mostly less than mu naught. Less than mu naught, so that we support H1, so we reject H0. So this is the p-value for this case. Actually, the possible value of V is truncated at 0. So 0 to 28 is possible values. So it's not like this. Yeah. And one-sided test with the other way around. So this is given by this. So this is Wilcoxon rank sum test. For two-sided test, so the so once we decided the p-values, then a p-value, then we can test based on that p-value. Yeah, and we can use the v sub alpha over 2 in a similar way as the t sub alpha over 2 or z sub alpha over 2. So based on this p-value, that we can test this hypothesis. Yeah, so the rejection region for one-sided test is just one side. So for this alternative hypothesis, we only reject if the sum of positive ranks is less than some threshold. And if H1 is mu is larger than mu naught, that means mostly we have positive numbers. So in such a case, if the sum of positive ranks is larger than some threshold, we reject null hypothesis to support H1. And again, this is one example. So we calculate the xi minus mu naught first, then we rank based on absolute value of this. Then we put negative sign if this deviation is negative. Then we calculate the sum of positive ranks and the sum of negative ranks. And for two-sided test, basically minimum of these two. This is important statistic. And if this is less than some threshold, we reject null hypothesis. And here is do you have any questions so far? And here is the code for Wilcoxon test. Just to be, instead of t.test, we can specify the Wilcox test, Wilcox.test, and you can specify just mu value. So it's exactly the same format as t-test. And we can get the V statistic and also the p-value. This is two-sided test. So alternative hypothesis is the true location is not equal to, so mu is not equal to 79,500. And p-value is actually 0.4688. It's very large, so we do not reject null hypothesis. Actually, the t-test does not reject null hypothesis. And Wilcoxon test is even weaker, so it's less likely to reject. So almost it's predicted that the null hypothesis is not rejected. So t-test, I think the p-value was 0.38. So it's slightly smaller than this because it's more powerful test based on stronger assumption. And one-sided Wilcoxon test is also possible with specifying alternative. If mu is less than 79,500 is the alternative, then you can put less here. Then you can get this. The p-value is just a half of original size, the two-sided test. But still, this is larger than 0.05. So H0 is not rejected.
I have a question.
And this is the other way. If alternative is mu is larger than 79,500, then we get p-value of 0.8125. So it's even larger. So we do not reject null hypothesis. So remember that X bar is equal to 70,495 or something. So actually the X bar is less than 79,500. So there is no way to support this H1. So H0 will not be rejected. Yeah, so that's the Wilcoxon signed rank test. And we have some exercise. And actually, the given sample size, we can calculate the probability of our test statistic is less than some value. So we can identify the distribution of V, actually. Then based on that distribution, that we can test. Yeah, and I think I have to take attendance. So